So I should start by explaining what are Ramsey problem and what is the Turan problem. So the Turan problem is the general study of how the number of vertices in the graph, how the number of vertices in the graph, how the size of the largest clique and the number of edges in the graph are related to each other. So I will state it in the following way. I will say the investigation is given the number of vertices in the graph, and if you are told that there is no large complete graph, no complete graph with t vertices, say, you want to study what are the possible values of the number of edges. So I'm trying to write the questions as general as possible. Given these two parameters, how does that one vary? So actually it's quite easy to see what is the minimum number of edges. It is 0, because you could have nothing in your graph. So that's not the interesting question. The interesting question, well, it ranges from 0, and the interesting question is what is the maximum? I'm trying to motivate all of these questions to see why people ask them. You want to know what is the maximum number of edges. And this is well studied. This is a theorem of Turan. And it says that the maximum number of edges, subject to these conditions, is achieved by the graph where I take t minus 1 parts of as equal size as possible of size n over t minus 1. Let's imagine that you could divide without having to round. If you have to round, you just round, and you connect every vertex which is in different parts. This is a complete multipartite graph. And I'll even write two particular values. If t equals 3, you're asking for graphs with no triangles, and that corresponds to the complete bipartite graph. That's about n squared over 4 edges, because you take two sides of size n over 2 each. And if t equals 4, I'm going to write this one. If you do the math, it becomes n squared over 3. That's not so interesting. Okay, so this is Turan problem. And this has been studied, questions of this nature have been studied for over half a century. Ramsey problem, again, in extremal combinatorics, usually you study how different parameters relate to each other. Ramsey problem asks to understand the interplay between the number of vertices, the size of the biggest clique, and the size of the largest independent set. So I'll write this way. Given the number of vertices, and you have no kt, the size of the largest independent set is what? So independent set is the opposite of a clique. Independent set is where you have a bunch of vertices and no edges inside. So again, this is easy on one side. Which side is trivial? I like to have people awake. Oh, I want to understand. Oh, of course, I want to motivate why people ask the question smallest. Because largest, oh yeah, size of, sorry. Oh no, that's right. See, this is a parameter. I want to say, what is the size of the biggest independent set you could possibly have? What is the size of the sorry, you're right. Largest independent set in the graph. So what I'm saying is, this number is a parameter of a graph. Given a graph, I can look at the size of the biggest independent set in it. And I want to ask, how can that parameter, the independence number, how can that vary if I'm given this and this? And there's an easy one. It could go up to n, number of vertices. It could be no edges again. So n is easy. N is the easy upper bound. And so the interesting question here is the min. So you want to know what is the smallest independent set smallest independence number you might have. So I'm just trying to motivate why people ask these questions in the first place. This is actually not as well understood as this one. So now I go to Ramsey-Turan, because Ramsey-Turan blends all of these things together. So you'll see that there are 4 parameters in total here. There is the number of vertices, which is the commonality. There's the no kt, which is the size of the largest clique, essentially, which is in common. And then here we have edges, here we have largest independent set. The way to blend them all together is to ask the following sort of problem. Is to ask, given the number of vertices, and if you're given that there's no clique of size t, and if you're also given that there's no independent set of size s, then you want to understand number of edges. The idea is that if you study the 4 parameters together, you might have a better understanding of them. So now here, neither side is trivial, but if you just ask for max number of edges, that actually includes both questions. What I'm trying to say is if you just ask this question, and you want to understand this for all the possible varieties of number of vertices, value of t, value of s, once you ask this question, you also know the answer for min, because you do the complement of the graph. That's why I'm trying to say this is the natural question to ask in this area. And actually many people worked on this question and a variety of questions related to it. And I will say the investigation was started by Vera Schoch, and Erdős worked on this, and many other Hungarians, not Hungarians, and so on. And actually, if you want to see a fairly current view of the situation, there's in fact a survey paper about 10 years ago. There's a survey paper of written by Simonovic, who is Hungarian too, and Schoch. And in this, a lot of the questions are spelled out. But the main question that people liked in this area was in a particular range of the parameters. So let me start with this observation to motivate why people cared about the question. So observe that in this Turan graph, if I have the number of vertices given and no kt, the way to make lots of edges, so in Turan graph, in Turan problem, the way to make lots of edges involves creating very large independent sets. The way to do this also makes big independent sets, where by big I mean linear in the number of vertices. Big here means a constant times the number of vertices. And in the entire talk is going to be the number of vertices. And will always be my number of vertices. Oh yeah, over there I also used it. So actually what they were curious is, suppose you put a restriction on the Turan problem. Suppose you still have this no kt thing and number of vertices, but suppose you force that all the independent sets are sublinear in size. So question, given number of vertices, given n vertices, no kt, and suppose you are also told that all of the independent sets are of size little o of n, so that's the notation for sublinear. Suppose you're given all this, then what is the maximum number of edges? Does the question make sense? This is a very natural question when you are studying all of these things together, because you wonder, is there a less efficient way perhaps to pack in lots of edges which doesn't involve making these big independent sets? I guess one reason this question gained traction is because the first case, t equals 3, is easy, and the next case is hard. So people like such situations. So if in the first case you are given that there are n vertices and no triangles, there's a result that says that if you have n vertices, no k3s, and all independent sets are of size at most are sublinear, then that implies that the number of edges is subquadratic. What this means is that you have no way of getting something this dense. In this extremal graph theory, we consider a graph to be dense if the fraction of the edges is a constant. This is like half of the total number of edges. This is 2/3 of the total number of edges. You can't even get any constant fraction. And so apparently, adding this condition really reduces your number of edges very substantially. And this I'll even show. So the proof of this, yes?
How do you get dense graphs? How big? So here you put t constant, but what if you put t?
I will get to it. I will get to it. So sorry I'm going slow. I'm just trying to help make sure all the students also follow. You probably are falling asleep, so I will try to do it as fast as I can. Okay, so I'll just prove this, because this is a very basic argument which has a more advanced version we use later. Proof of this. So let's denote alpha to be the maximum independent set size. That will make it easier to write the proof. Maximum size of the independent set inside your graph. The key observation is that having no triangle is a very strong condition. Then, all of the degrees in your graph are also less than or equal to alpha. And the reason for this is because if you have a vertex and it has some neighbors, there's no triangle. So since there is no triangle, all of the neighbors of the vertex, there's no edges here. Is this clear? And that's an independent set. But I told you that the biggest independent set was alpha. Sorry, this is the maximum independent set in a graph. I'm given a graph here. So that means that all of the degrees are less than or equal to alpha. And that implies that by standard counting argument, the number of edges in the entire graph is at most, you take the number of vertices times the biggest possible degree, divide by 2. Standard. And I told you that this is sublinear. If the alpha is sublinear, then this is at most subquadratic. Okay? So the K3 is very simple. It fits in this one line. But then the next question was, of course, actually just like the one that was asked, what happens? What happens for larger t? And the first one is for t equals 4. So for a couple of years, people tried to create graphs. People tried to construct graphs which had number of vertices, no K4, sublinear independent sets. And they were trying to make graphs with a bunch of edges to see if it could be quadratic. So for K4, people tried to construct graphs with no K4, all independent sets, little o of n, and a quadratic number of edges. It was unsuccessful for a while. And then there was the theorem of Semeredi. From the 70s, 72. So actually, it wasn't even clear what the upper bound was. It wasn't even clear that a certain number of edges would force you to have big independent sets. But actually, he proved a statement which I will write in the following way, that if you have no K4, all independent sets, little o of n, then the number of edges is at most, you can do a better bound than n choose 2. So n choose 2 is trivial. Every graph has at most n choose 2 edges. You can write 1/8 plus a little bit times n squared. Okay? This is confusing because there are too many little o's everywhere. I'm going to restate this. So this is the classic way that it's been written. I'm going to restate this equivalently. What he proved is that for any epsilon, well, I will just write the statement. If you have no K4, and if you have number of edges bigger than this, 1/8 plus epsilon, n squared, then there exists a linear size independent set. I just basically turned the statement upside down. Implies there exists an independent set of size at least n times a constant. Now, there's a constant because there's an epsilon here. The constant depends on the epsilon. The constant happens to be 1 over 2 to the power 2 to the power 1 over epsilon squared. That's what the proof gave. Okay, this n is on top. So the point is, if you have a little bit more than n squared over 8 edges, you will already have linear size independent set with this sort of dependence. I will say two things. The first is that actually this was a milestone. This theorem was a milestone because it was the first application of what is called the Semuredi regularity method. So this theorem, it was the first application of the regularity method. And the Semuredi regularity lemma is the same one here. I will actually not discuss this because it might be beyond the scope of what some people are in the room, and it would take a long time to introduce from scratch. Okay, now actually this didn't answer that, because this is telling you that you can't have tons of edges. There's still a question to try to construct something with a quadratic number of edges. And people kept trying, because people thought that, people actually tried to prove the other way. People tried to prove that maybe you can reduce this all the way down to a subquadratic and get the same kind of result. People wanted this result with a 4 instead of a 3. But it was a surprise when 4 years later, Bolabash and Erdős proved that actually you can get a quadratic number of edges. So from 76, there exist graphs with no K4, so I'll write K4 free graphs with, I'll write 1/8 minus little o of 1 and squared edges, and all independent sets sublinear in size. So actually then the answer to your question is you only need to go to 4. And this was a surprise. People really were trying to prove this, improve the 3 to a 4. The second surprise on this is it's the same 1/8. And that was using some new regularity method, which was not well understood. This used high dimensional geometry. I will actually show this. I'll show a bunch of historical stuff, and I will also show you some new arguments. But the historical stuff is nice. I'll show you this. So the proof of this, we now have to make the construction. The way you make the construction is you have to write a graph. A graph has n vertices. I will write a graph, draw a graph, by taking two spheres of high dimension. I will not tell you how high, but I take two spheres with some, they're not three-dimensional spheres. The dimension, I say high, is because it will grow as n goes to infinity. So we have two high-dimensional spheres. And I will distribute n over 2 points on the surface of each sphere. There are n over 2 points on the surface of this one, and there are n over 2 points on the surface of this one. They don't have to be distributed the same way. I will actually think of both of these spheres as having the center at the origin, even though I drew them separately. Now I need to make a graph. I need to tell you what to connect. So the way you draw edges is between, within a single sphere, you will draw an edge if the two vertices are far apart. So these are connecting far apart vertices within the same one. The edge is if the distance is bigger than 2 minus some parameter delta. There will be some parameters like the delta and the dimension. I will not go into that detail, but if you work those out, that's how you get these little o's. So you do the same here. You also connect two guys. Maybe I'll do these. You connect two guys if the distance is bigger than 2 minus delta. Okay, now you also will connect some edges that go back and forth. And the way you do that is you will take, for convenience I'll pretend one of them happened to be the North Pole. You will connect the vertex to anyone else where the distance is less than square root 2 minus delta. By the way, these are unit spheres. I'm sorry, that's why there was a 2. The biggest distance is a 2. And this is square root 2. This construction has very nice properties. So I'll clear this. So I have several things to verify. Maybe I go in order. The first is K4 free. So why this thing is K4 free? Well, delta will be a small thing. So in order to make a complete graph with 4 vertices, I actually cannot put 3 of them on the same sphere because they are too far apart. You cannot make a triangle. So the only K4 you can make is to use 2 points. I'll actually superimpose the 2 spheres. I'll say there are 2 points that are far apart like this, and then 2 other points which are also far apart like this. Does that make sense? I drew them both on the same place now. And both of these sticks are of size at least 2 minus delta. And in order to have a K4, well, there were 2 points here and 2 points here. Those are far apart. But between any one here and any one on the other side, they have to be close together. So I also require that these distances are less than. I'm trying to show why this does not exist. There's no K4, because if there's a K4, it looks like this. Like this. So all of those dotted lines have to be short. And this is actually a Euclidean geometry problem. Because if you try to put 2 long sticks such that all of the endpoints are close, what you do is you make your 2 sticks to touch each other. They should go through each other. You make them to be right angles to each other. And it's a simple Pythagorean theorem. Even if you had them going right through the middle, this length is 1/2 minus delta over 2. And this is 1/2 minus delta over 2. So this guy, sorry, these were bigger. So this guy is at least the square root 2 of that, which is equal to the square root 2 that we had there. Just a second.
Maybe not half. 1.
1. Thank you. These are 1. Yes, thank you. Yes, those are 1 because it was 2. It was half of 2. Yes. Good. So you have this 1. And then what you have is the 1. So you keep the square root 2 minus a delta over root 2. So you're missing less. Very good. So this is actually too big. This is bigger than root 2 minus delta. Because when I put that there, I put that. Yes, very good. Okay. So this is why there's no K4. Next thing, it claims a lot of edges. This is actually important. So the n squared over 8 is very much like n squared over 4. So I'll write lots of edges. So if I had a complete bipartite graph going back and forth, then I would have, actually the only important thing is at least here. But in any case, if I had a complete bipartite graph going back and forth, I get n squared over 4. 8 means I want to say I'm getting at least half of them. So actually by lots of edges, what I want to show is that every vertex is adjacent to at least half of the other side. At least about half. It can be missing by a little bit. At most, at least about half of the other side. But that's why square root 2 is picked. Because if you have a particular vertex at the North Pole, the square root 2 is exactly the distance to the equator. So the guys that you are adjacent to are the guys that are just above the equator on the other side. So maybe I'll write this way. So you have a guy here, and who he's adjacent to is on the other side, just above the equator, all of this, which is half. Okay, so that's how you get this 1/8. And the last part is independent sets. Well, an independent set in the whole thing is of size at most twice the independent set on one side. Size at most twice of the biggest independent set on one side. On one sphere. Because you can at most put 2 together. And now what is an independent set on one sphere? On one sphere, now I'm saying I have a bunch of points. Independent set means that they cannot be too far apart. I cannot have any distances like this. So I have a bunch of points on the sphere such that the diameter of this point set is less than or equal to 2 minus delta. And it turns out that there is a isodiametrical inequality in high dimensional geometry, which says that the maximum, and this I won't go into, but if you have this, then by an isodiametric inequality, this number of points is at most the number if that was a spherical cap with the appropriate, it's at most if that was a spherical cap with appropriate diameter. So the number of points is at most the number of points in the particular spherical cap of this diameter. Okay, which at first looks a lot like this. It seems like you have a lot, but actually that's why you choose high dimensional sphere. There's concentration of measure phenomenon, and if you work out the details, even though this looks like that, this is actually a very sublinear size, even though this was about half. And that's because a delta becomes a square root delta, but I won't go into that. So you have this, and then these spherical caps are small. Small means little of 1 fraction of the surface area. Okay, so then the next thing to do is, so this is now proved, and this was nice. I will now want to talk a little bit about the proof of this thing, because we are going to talk about this. The main result starts around here. So on this problem, I will not show you the whole proof because it uses this regularity method, which I'm not going to introduce, but I'll show you one key step which is involved, because there was a 1/8 floating around everywhere. The fact that there is a 1/8 means that somehow we have to be forcing a lot of degrees to be half of things. And I want to show you where half arises naturally. So there's a lemma. If you're trying to prove the other direction, so this is useful to show that if you have at least 1/8 plus epsilon and squared edges and no k4, you want to use this to show find a large independent set. Useful to show that if you have this and this, then exists a linear size independent set. Okay, and the lemma, I didn't say what is the lemma statement. The lemma statement says the following. Suppose I have two pieces, both of size, say epsilon n. Suppose I have two pieces of size epsilon n. Okay, these epsilons will be different from that epsilon, but I just want to show you a lemma. This lemma is true, and it will be useful to show something like that. Suppose I have two things like this, and suppose that I know that that the density of edges, I can look at the density of the edges going across. If I know that the density of the edges is, I know that this is more than 1/2 plus epsilon, then this is going to imply, the lemma says if I have two pieces like this with a density more than half, then there exists either a K4 or an independent set of size at least epsilon squared n. Okay? So the idea is that there's something special about going above density half. These linear size things come actually from the regularity lemma, but I just want to show you the lemma because the argument is useful later. Does the statement make sense? This is just a statement about graphs. A graph where I have two pieces like this with density. And density is I take the number of edges and I divide by those two. There's the square of that size.
The epsilon at the epsilon n and half plus the epsilon is...
These are the same. So basically, you should ignore what is written there. I wrote here a true statement, and it can be used to prove this with a different epsilon. Okay? So the proof of this is actually quite straightforward. The first step is standard, which I won't go into. If you have the fact that the density is at least something, you can easily show that there exists a subset of the left side, which is of size epsilon squared n, such that not only is it that the density across on average is this, but that every single vertex has, I'll write, cross density bigger than 1/2 plus epsilon over 2. So this is basically going between min degree and average degree, if you've seen these sorts of arguments before. Why is this useful? This is useful because now either this is an independent set. I want to show this thing. If the left is an independent, then I'm done because I got an independent set epsilon squared n. Right? That's one of the objectives. Done because of this. So there's an edge on the left-hand side. So I can make an edge. But now this edge has density, each vertex of this edge has density across more than 1/2 plus epsilon over 2. So actually by basically pigeonhole principle or any kind of a union, like Venn diagram union thing, you will find that these two pieces have to overlap. Who these two guys are adjacent to has to overlap. and the amount that they overlap by has to be at least the density, well actually twice this, is twice epsilon over 2, which is just an epsilon, times, so this is the density component, and then times the size of that side. Okay, so this is basically just saying if I have two big things bigger than half, they have an overlap. You can check the constants, that's not the most important thing. But now inside the overlap, if the overlap is independent, then you're again done, because this was epsilon squared n. Else, there's an edge inside. But the edge makes you a K4. Let me label them A, B, C, D. Then you have an A, B adjacent, a C, D adjacent, and these are common neighbors of both. Okay, so this is the basic argument. Okay, so now we want to go further. I will not show the regularity lemma proof, but I will say people were curious whether you can do better than this, because it's a bit strange that this regularity-based method using that lemma meets the geometric construction. So there were a number of questions which people asked actually many years ago. The most interesting one, which is how we got attracted to the project, was the question of, is the regularity lemma necessary? Of course, I haven't told you what the regularity lemma is, but I hope a number of people know what it is. The biggest question, which we were interested in, is the regularity method essential for such a proof, for the result? And in fact, there was a there was a survey on the regularity lemma. If you want to learn about regularity lemma, the recent regularity survey, and this is by a number of authors. I remember Komlosh, Ko-Fande, Shosh, and Simonovitz. Looks like I was out of order. Actually, it was Semeredi. They actually surmised that it was essential. In this survey, it was written that it's believed that it is essential. Because of the 1/2. That's why I went to stress the 1/2. And actually they had a philosophy. The philosophy was that if the extremal constructions, if the best constructions, like this Bolobash-Erdős graph, if the best constructions have these, actually it goes into the regularity method, but I'll say it has parts, these are regularity parts, but parts with density between them which are not 0 or 1, not close to 0 or 1, this is not asymptotically 0 or 1, then essential. Then the regularity is necessary. So this actually, if you know what regularity method is, it's that you would say, take the construction, apply the regularity lemma to it, look at the partition, and look at the densities between the parts, and the philosophy was if it's not 0 or 1, then it's necessary. In contrast, the Turan graph, if you take the regularity partition, it has these parts, and between them the density is full, and within the same part the density is 0. Okay, so that was one question. There was another question of Bolobash and Erdős. Again from the 70s. So their graph has almost n squared over 8 edges. These results say that if you have more than n squared over 8 edges, something holds. So the question was, for example, the key question is, if you have at exactly n squared over 8 edges, if you have no K4, what can you say about the independent set size? Independence number, how big must it be? And there were also questions along this line, also in the same paper. Are there actually better constructions? Why should it be that this funny high-dimensional geometry thing should be the best? Are there better constructions to get more than n squared over 8 minus a little bit? The problem is that it's yes.
Can I ask some questions?
Oh yeah, of course.
So in the Bogobosh-Erdős construction, what is the regularity distribution?
So I'm not entirely sure, but it definitely has a lot of the 1/2 parts in it. Just because the way it's constructed is that everything is going to half of the other side. I also know that it has to be that way because in the if you prove this statement, the full statement of Samareddi's result, which I'm not showing, you will actually conclude that you have to have these large zones of 1/2. Yes, and that's why I went to so much effort to hammer out a 1/2. Okay, so actually in our paper we answer all of these questions. So the first result. Yes.
One more thing. So what does better construction mean?
It was 1/8 minus a bit times n squared. Can you get more? Better mainly is can you surpass n squared over 8? Right, so the constructions from before were 1/8 minus a bit with no independent set. Well, I'll write all independent sets, little o of n, and we only know that if you're above by a bit, you have independent sets. Okay. So actually, we answered these questions, and with Jacob Fox and Yufei Zhao, the first result we want to say is that actually the regularity method is not essential. We found a way that went around all of this. I should say actually a lot of people have been trying to remove the regularity method from a lot of classical proofs, mainly because the regularity method gives you an easy way to, relatively easy way to get a result, but it gives you terrible bounds. There was some bound here which was 1/2 to the 2 to the 1/epsilon squared. Actually, that's a great bound. But usually the regularity lemma gives you bounds which are tower functions of extreme height. So people wanted to remove regularity method. And it turns out that you can in this question, surprisingly. And when you do, you get a better result. So I'll write it in the following way. Which page am I on? Yes. So with no regularity at all, if you have at least 1/8 plus a bit n squared edges, and you have no k4, this is the beginning of the Samareddi statement. The end is different. Without this, if you have this and this, then there exists an independent set of linear size, of size at least n times. Before it was 1/2 to the 2 to the something. Now it's just actually linear in the same epsilon. This is a small constant, 10 to the 10, in the grand scheme of things. So when you have a better technology, not better, better is the wrong word. Regularity method is a great technology. But when you have a more elementary technology, you are not bound by the large dependencies that are inside the heavy machine. Okay. But actually, if we also discovered that if we could use the regularity lemma once, whatever that's supposed to mean, with one application. So with one application of regularity. So this is, first of all, we thought this was interesting because it already answers that no. But the next thing, if you use one application of regularity with a fixed precision, I'll write 10 to the power minus 6. So when you apply the regularity method, you usually say, I want things to be epsilon regular, where there's some epsilon, and it's not this one. And what I'm saying is that our precision is just 10 to the minus 6. So actually, the statement of regularity method lemma with precision this, you could actually write down. It's actually something which you could decode. So it, in some sense, it's not the full regularity. With this, then under the same conditions, there implies there exists an independent set of size at least n times, not that, but 2/3 epsilon. So suddenly you really get very, very close. Well, we don't know what close means. You just get small numbers. But you'll see in a second why I said close. We have this. Actually, this only holds. You also need something. You need to also have, you can't use it with huge epsilons. Epsilon less than some absolute universal constant. This is not so interesting. Okay, so we have this. So now once we had the technique that could get so much closer, we decided to attempt the question at n squared over 8. Because previously the regularity method wouldn't let you get that close. So the next thing I want to write is what was previously known at n squared over 8. The previous best result in that regime was by Benny Sudakov in the early 2000s, 2003. And actually his result is a bit more general. It's not n squared over 8. His result was as long as you have a constant fraction of the edges, like a quadratic number of edges. So for any constant c, there exists some other constant c, such that if you have constant n squared edges and no k4, it's always at least, if you have this many edges and no k4, then there exists an independent set of some large size, but where large is at least this. Size at least, I'll write n over e to the power the other constant times the square root of log n. So this sort of a quantity comes up quite often in extremal combinatorics. The way to think of this is that if it was e to the power constant times log n without the square root, e to the power a constant times log n is n to the power the constant. So the way to think of this thing, since we have a square root log n, this thing in the denominator is weaker than n to the power anything. Right? So basically the way to read this result is that the way people usually write this result is that it's at least this, and as a consequence it's at least n to the power 1 minus little o of 1. Meaning you can, maybe you can't get a, well, it's not known that you can't, well it wasn't known that you can't, but it was known that you can get almost a linear size independent set at any constant c. And in particular, if you plug in 1/8 for here, you will get something. So then our result So then we went into the n squared over 8, and I will write the result in the following way. If you have at least n squared over 8 edges, you have no k4, then there exists an independent set of size at least. It's still almost n, but this time the almost is this. So even if you're not familiar with this sort of notation, this should seem very close to n, because you're short by just a logarithmic. Actually, we can prove slightly more. This is not so important, but we can get a little bit more. In any case, there is a method now which we developed to do this. This is a twist of a standard method that has been called dependent random choice. That's what I want to talk about at the end. So now we have all of these lower bounds on the independent set size. So then we went back to revisit the Bolobash-Erdős construction, because the Bolobash-Erdős construction was everything was written with little o's. So actually, I won't write it as a theorem, because we just went over their proof again. If you're careful with the Bolobash-Erdős, so careful Bolobash-Erdős, actually you can find the following results. You can find that there exist k4 free graphs with, I'll write 1/8 minus a bit edges. So this is sort of what they had, except they had here a little o1. We're going to say exactly how big, or the maximum size of the independent set. There exist these graphs with this many edges, and with all independent sets of size at most. So first I'm going to write Benny's result. So it's known that by this result, it will be at least n over e to the power some constant times the square root of log n. It's known that it's at least with some constant here. We actually showed it's at most, where you actually put the same epsilon here, and you correct it with a log-log. This is not so important what is the function itself. What is important is that it is very close to the best lower bound. Then we found out that we could also inflate the Bolobash-Erdős construction to answer the next question of can you get more edges and still small independent sets. So there is a technique to do this, to say there exists k4 free graphs at exactly n squared over 8 edges, where all of the independent sets, so basically I'm doing all the complementary bounds to every result that was stated earlier. All independent sets, we want to be less than or equal to something. Over here, we know that it's going to be at least this, and actually we get very close. So I'll write, instead of the log, square root log. So it's up to a square root log factor, and there's some correction here. Log, log, n to the 3/2. This is not so important. What's important is that the square root and the not square root are close. And it also turns out that you can inflate this even further. So first of all, you now already know that at n squared over 8 edges exactly, you cannot hope to get a linear size independent set, because here's a construction with sublinear size independent sets. It's also known, well, if we continue the inflation for any epsilon, which is between, there's some function log log n to the 3/2. These are not so important, you don't need to copy these down. And up to 1, there exist graphs with k4 free and with 1/8 plus epsilon n squared edges, where all of the independent sets are of size at most. There's a result over here, which is n times 2/3. Actually, we can write n times not 2/3, but 3 epsilon. So actually, this was very close, which we were surprised to find out. So again, the exact details of these functions are less important. What is more interesting is actually the proofs, which well, a certain idea in the proof, which I now want to talk about for the rest of the time. So are the results clear, first of all? That's why we call this looking into the critical window of the Ramsey-Turan problem, because the 1/8 was the misunderstood part, and now we understand it fairly well. So the last bit, I want to talk about a method which is called dependent random choice. So one reason I like this particular result is it extended the technique which I'd found to be useful for many extremal combinatorics problems. And there's in fact a whole survey on this thing called dependent random choice, but there's an extension to it that we discovered which let you get a substantially better result. So first I'm going to talk about this result. This result uses the standard dependent random choice. So let me put it this way. Suppose you're trying to prove a certain bound at n squared over 8. Suppose you're trying to find a large independent set. So we are trying to find a large independent set of size at least epsilon and epsilon n. Okay? There's no epsilon here anymore because I'm really looking into the critical point. Suppose you want to do this. Then the way you would do this is you would assume, for contradiction, that all of the independent sets were smaller than epsilon n. Now I will say our technique, which let us get all the way out to here, actually can be used to find the following structure. I won't show you how to find it, but I'll show you what to do after it. Using this assumption, there exists a structure in the graph. The graph has some linear size number of vertices. I think it's 16. It's not really important, but it's a 16. There's some piece here. Inside the graph, some other constant over here. I'll call this the left-hand side. I'll call this the right-hand side. And we can find this thing in our graph such that every vertex on the left has a good density across. So every vertex of the left has density across to the other side, at least. Now remember, there was something at the beginning. It was about if the densities are bigger than half plus epsilon, then you are done in some sense. Actually, using our technology, if you make this assumption here, you can get something like 20,000. Constants are not important, but I'm writing down things that are true. So what I'm trying to say is if you make this assumption, actually you'll find very large sets inside your graph such that there are very close to half densities going across. Okay? You can find this. Then I will say, what's the goal from this sort of thing? Suppose we seek the following. We seek a subset L prime of the left-hand side of size. This is the dependent random choice technique coming up now. Of size at least epsilon n, such that every pair of vertices of vertices x and y inside your L prime, this is not an epsilon, inside L prime, has at least epsilon n, okay, I'll write co-degree, has co-degree at least epsilon n in the right-hand side. Co-degree means that if I have two vertices x and y, I'm looking at all of their common neighbors. That's what co-degree means. So I seek this. There's a reason I seek this. Why? Suppose I found such a thing. Then this should look a lot like the argument I gave at the very beginning. Because then what can you do? Your L prime, you have here your L prime, it's already of size epsilon n. So I'm going to do this fast because we already saw this. This piece, if it's an independent set, I'm done because I was seeking this. Right? So this is the same argument as before, not independent set. I have this. Here's my right. Oh, but I know that every pair of here, so I happen to choose this one, but every pair has co-degree in the right side at least epsilon n also. Same thing happens as before. Either this is independent set, I'm done, or there's an edge. And this was the K4, A, B, C, D, which we had before. Okay, I did that fast because I did it slowly earlier. So the whole game is to find lemmas of this form. These types of lemmas are actually very useful in doing lots of things in extremal combinatorics. And the way they have classically been approached is using a technique called dependent random choice. So I'm actually going to quickly show how you use dependent random choice to prove something like this. And then I will show how you twist it to get our stronger result. But if you're curious about dependent random choice, this is a very useful technique if you ever do extremal combinatorics, so it would be good to look at the survey about this subject. Okay, so I'm going to prove it in a cleaner setting. This setting has some funny constants here and some funny thing here. I'm going to just write down the core, the important part. So I'll look at the following situation. I'm going to say there are n vertices on the left, n vertices on the right. So don't worry about the constants anymore. I got these two things. And suppose I'm going to also tell you that every has density to the right, at least this. I'll say everyone has density to the right. Every vertex on the left has the density to the right of at least half. Okay, just for simplicity. And then you will see how all of the different constants could be tuned later. Here's the setting. And I seek a subset L prime of L of size at least epsilon n. The question is what epsilon? So the question is, so I seek a set which is fairly big such that all of the pairs in L prime have co-degree at least epsilon n. So the important thing in this statement is that these two are the same numbers. Whatever is here is the same as here. And the question is, in this sort of setting with n, density half, what's the biggest epsilon you can find? The question is, how big epsilon can you guarantee for this to be true? Can you use, and this statement is always true, always holds. Is the question clear? I'm now trying to understand the limits of a particular type of technology. And the technology is something that lets you find these large subsets with big common neighborhood. And I want to know what is the absolute limit I can put on these epsilon. The better a limit you put here, by the way, the better an answer you will get here. Because these epsilons become those epsilons, and that's how you try to find big independent set. Okay? So now let's talk about the original proof of this thing. It's actually very nice. So the original proof of this type of statement, it's called dependent random choice. So you must choose something randomly, but not independently. So what you do is you pick t. I have to specify what t is in a second. Pick t vertices of the right-hand side independently. And everyone has equal chance, uniformly. Does that make sense? So I picked some number, and I will tell you what this number is later. Pick this. Now what I do is I first let L prime to be everyone who is adjacent to all of them. So L prime is the vertices of L that are adjacent to all of the t picked. So for example, if I pick t to be 3, then I see I see which people are neighbors of all 3, and I pick those for my L prime. Is it clear? This is why it's dependent. This part is independent, but that's dependent. But I can't just do that, because I said that this has to have some nice codegree property. So I need to fix it. Then you fix it. How do you fix it? You say, for every pair of x and y that happen to be in your L prime, which has codegree too small, smaller than epsilon n, I will throw one of those two vertices out of L prime. For any pair which I pick like this, I arbitrarily choose x or y. I'll say x. You delete x from L prime. I could potentially erase the whole L prime, and then I would have nothing left. That would be bad. But if I have anything left, it satisfies the conditions. Right? So now I need to understand what happens here. Okay, so now we use probability. So in this sort of problem, we use methods from extreme-ball combinatorics to geometry, and now probability comes here. I'll define some random variables. X equals the number of vertices originally picked for L. Originally for L prime. Okay? So the way you can study this, you can write the expected value of x. And the expected value of x, well, let's see. So every vertex, here, I'll write a vertex, is neighbors to at least half of the other side. So what's the chance that it's picked? It's picked if all t of the guys sit inside here, right? And that expected value I'll write is at least the number of vertices on the left times the probability that all t of your vertices are inside. This is standard linearity of expectation. Okay? Good. That was actually easy. Now the next thing we need to do is y is equal to the number of deletions. So actually the number of deletions I can write this way. It's at most the number of pairs in the whole set L such that they have less than epsilon and common neighbors, but somehow both were picked. Pairs x, y, but somehow both x and y were picked. Does this make sense? This is how many things I have to delete. Go over all of the pairs in the L, see how many times I have this. This might be an overcount, because I might also have x, y, which aren't in my L prime. But what I can write now is expected value of y is then less than or equal to, well, the number of pairs in the left with this property, it's at most, I'll write n squared. You could write n squared over 2. And then what I write is times the probability. The probability is if I have an x and a y on the left, such that their number of common neighbors, their common neighbors is less than epsilon n, how do they both get picked? To get both picked, you have to put all t in the common neighborhood. Is it clear? So the chance here becomes epsilon probability that you sit inside this to the power t. Now you play these two things against each other. So probabilistic method tells you that the expected size of L prime at the end is at least, you can use linearity of expectation, it becomes n over 2 to the t minus this correction, n squared epsilon to the t. And I will just say, if you want to get the bound that was originally written from Benny-Sudakov, what you choose is you choose t to be the square root of log n, and you choose epsilon to be something like e to the power minus 2 root log n. That's not so important. I'm just going to write something. I think that's correct. Let's see why it's correct. Because if I take epsilon to the t, this thing here gives me a n to the power minus 2, cancels that. And what's left here is a n over 2 to the t. So what's left is about more than n over 2 to the square root of log n, which I said I want to compare it against epsilon n. This is bigger than epsilon n because of choice of epsilon. So I'm saying you can play with the constants. And what you find out is the expected size of L is indeed what you wanted it to be. L prime is at least what you want it to be. And finally, how to twist this. So first of all, why do you want to twist this? Suppose I change it very slightly. So if I change the half to any other constant, do you see that you would kind of be able to do the same thing and get a different constant here? So if I use, instead of half, like a quarter, do the whole thing, I will get it with epsilon being e to the power minus some other constant root log n. This is why Benny's result says for any density cn squared edges, you get this with different constant. But I'm going to choose a particular constant. I'm interested in some region very close to half. And what I thought was strange when we were in this question, and what motivated the discovery is, suppose it was 0.51. Suppose. The same argument will give you this with, instead of -2, some other thing. Can someone think of a different way, though, to prove a better epsilon? Well, if every pair has density at least 0.51 across, why don't I take the whole left side? If I take any two on the left side at 0.51, then they already got, any pair already has common neighbors at least 0.02 of the right-hand side. That's already linear. I didn't have to do anything. But somehow this proof only gives you this sort of a bound. Actually, you should have a much better bound. So I'll just say the idea of the twist, and I won't go into detail on it because we're out of time. But if you actually have density at least 1/2 minus a bit, this was the key contribution. If the density is at least half minus a bit, you want to understand better. You don't want this kind of a bound. Because if you are doing the problem that we have 1/2 minus some bit. We want to get a bound which is not looking like this, e to the power minus. We want a bound which is something like n over log n, with times log n. The trick is you pick these independently uniformly. But here, you don't say adjacent to all. You say, of the ones picked, at least 1/2 plus epsilon t of them picked. So just barely more than half of the ones that were picked. Before we insisted all. Still, we need to clean our set at the end. What changes? Now, the chance that you pick a vertex for the left-hand side, you have everyone with some good density. So I'm going to look on an average vertex on the left. It's got some good density to the right. This is about 1/2 minus epsilon, fraction of the right. What you can write here, I'll write it in terms of probabilities. You can write here, instead of an exponentially decreasing thing, you can write n times the probability that if you take a binomial random variable, you do t trials, because that's how many darts you're throwing on the right side. And the chance that they will sit in here is 1/2 minus epsilon. This is the neighborhood of your guy. And you're asking, what's the chance that the number of them that sits there is going to be a binomial random variable. And I want to know what's the chance that this exceeds a little bit more. Is this clear? This is really good. Because if epsilon is small, this does not decay exponentially. Because now we have a probability distribution, binomial distribution. And we are asking if you are, here's the mean. The mean is at this times this. We're asking for the chance that you're above the mean. This is not decaying exponentially. So you could potentially get more for x. Why? I mean, now for y, you have this. Now you ask, what's the probability that both x and y are picked? So I have an x and y. They have a small common neighborhood. How can it be that both are picked? If both are picked, let's look at the two neighborhoods of the x and the y. It's basically a Venn diagram again. So I have the two neighborhoods. This is the neighborhood of x. This is the neighborhood of y. And somehow I'm picking t vertices. T vertices got picked. Oh yeah, here's the whole right. The right is much bigger. I picked t vertices. How can it be that in this circle, this big circle, I need to have picked both x and y. So I need to have more than 1/2 plus epsilon t in this circle. I also need to have more than 1/2 plus epsilon t in this circle. If I have t vertices I'm picking, and here's a Venn diagram, and 1/2 plus epsilon t are there, and 1/2 plus epsilon t are there, how many must sit in the middle? It's like twice. Very good. Then the number in the middle, you must somehow have picked at least twice epsilon t in the middle. Okay, the twice is very important. Because I said that there are common neighbors, the middle has size epsilon fraction of the whole thing. This is epsilon fraction of the whole thing. So I'll just quickly write, this becomes n squared times the probability that if you take binomial random variable, t trials, epsilon chance of success, that you got more than twice what you were supposed to have. And is this okay? So basically you make your t tries, but since the common neighborhood is so small, your chance of success is only the epsilon, but somehow you put twice epsilon t in there. The average of this binomial is now here. This is epsilon t, and now you're going twice far. there's a Chernoff inequality. There's concentration inequalities. If you're deviating from your mean by more than a constant factor of your mean, this probability is actually exponentially decaying in t. So I'll write inside here, you get an exponential decay in the epsilon t. And so if you play the parameters against each other, by not losing so much here and still having exponential here, you get the gain. So I just wanted to show this technique because it could potentially be useful for other applications as well. And thank you for paying attention. Yeah.
Thank you. Do you have any questions?